Hello students, welcome back to next session. So in this session we are going to discuss subcooling and superheating and their effects on refrigeration, vapor compression refrigeration system. So as I mentioned earlier, vapor compression cycle, PHTS diagrams, deviations from theoretical cycle, subcooling and superheating, effects of condenser and evaporator pressure on COP, multi-pressure system, low temperature refrigeration system, cascade systems, problems. We have compressors and condensers, and we have expansion or throttling devices, evaporators. So next is effect of liquid subcooling in vapor compression refrigeration system. This is the diagram. You can see here TS diagram and PH diagram. This is pressure enthalpy diagram, and you can see here there are dotted lines. These lines represents the actual cycle. Actual cycle from 1 to 2 it is known as compression process, and it is normally, and it should be normally isentropic process. Isentropic process 1 to 2, and from 2 to, actually in actual cycle, in practical cycle, it is happening from 1 to 2 dash. So 2 dash to 3 dash, it is actual cycle. From 2 to 3, it is the ideal cycle, ideal process. From 3 to 4, it is the actual process. From 3 dash to 4 dash, it is the 3 to 4, it is ideal process, and 3 dash to 4 dash, it is actual process. So now this is the condensation process is taking place. Condensation is taking place from 2 to 3, and expansion process is happening between 3 and 4, and the evaporation process is taking place between 4 and 1. And these are the four steps. Similarly, here we can see 1 to 2, it is compression process. So here 2 dash is happening here. During condensation from 2 dash to 3 dash, from 3 to 4, it is the expansion process. From 3 to 4, it is expansion process, and four processes are happening in cyclic manner, and this is the actual and ideal cycle. Both are shown here, and let me give you small comparison in a very short manner. So this is the process. You can see here, students, process 1 to 2 is compression. 1 to 2 is compression. It is ideal cycle is actually isentropic process. But here, if you see the isentropic process, but in real, it is entropy increases from 1 to 2 dash. So 1 to 2 dash, entropy is getting increased, and this is the higher energy consumption taking place in actual system, in actual implementation. The higher energy consumption taking place during condensation process 2 to 3, constant pressure process, it is ideal cycle. In ideal cycle, it should be, it is a constant pressure process, but in real, in actual process, it is a subcooling process 2 dash to 3 dash, and it prevents refrigeration flashing, refrigerant flashing. So that is the subcooling advantage here, and that is the effect on practical situation. And the 3 to 4 is expansion process. It should be isenthalpic process 3 to 4. The actual is isenthalpic process, but entropy increases 3 to 4, 3 dash to 4 dash, the entropy is getting increased, and it affects refrigerant flow. Possible frosting also taking place. Frosting it is a freezing process. Possible frosting is also is possible here. Evaporation process 4 to 1. So 4 to 1, it is evaporation process. It is constant temperature process as well as constant pressure process. So in ideal cycle, it is constant temperature, but in reality, it is pressure drops. There is a slight superheating also. it impacts cooling efficiency. So that is the ultimate effect on this 4 to 1 process. So this small comparison, please keep in mind, students, so that it will be very useful and handy while solving problems in forthcoming sessions, students. So next is subcooling or subcooling effect, and here you can see the subcooling is the process of cooling the liquid refrigerant below the condensing temperature for a given pressure. So this is the subcooling process. It is happening between this 2 dash and 3 dash. So that is the subcooling process. So from where the vapor is getting the phase change into liquid. So you can see here in the figure, the process of subcooling is shown between 2 dash and 3 dash. As an evident from the figure, the effect of subcooling is to increase the refrigeration effect, the refrigerating effect. So this is the refrigerating effect is increased due to the subcooling effect. The subcooling results in increase of COP provided that no further energy has to be spent to obtain the extra cold coolant required. So here subcooling results in the increase in COP. So subcooling is actually a desirable process. It increases the COP provided no further evident or no further energy has to be spent. So that is very important. No energy should be wasted and has to be spent to obtain the extra cold effect, that is the extra cold coolant required. So that is the subcooling process advantage. When you are applying this, there will be increase in COP. That is a desirable characteristic or desirable workout we are getting out of this. So liquid subcooling here in vapor compression refrigeration system, it refers to reducing the temperature of the liquid refrigerant below its saturation temperature at a given pressure. This is done to increase system efficiency and prevent flash evaporation before the refrigerant enters the evaporator. So here the flash evaporation before the refrigerant enters the evaporator. So that is it should prevent the flash evaporation. That is the very important aspect of this. And if you see the significance of liquid subcooling enhances refrigeration effect. The refrigeration effect is increased as the refrigerant absorbs more heat in the evaporator itself. So in evaporator we are getting the subcooling effect, and it absorbs heat, and that heat can be sent out to the environment, and prevents vapor formation in the expansion valve. So if the liquid is not subcooled, some of it may flash partially evaporate before reaching the evaporator, reducing the cooling efficiency. So that is the effect of this, and reduces compressor load. So here, since more refrigerant stays in the liquid form, the compressor handles less vapor volume, improving coefficient of performance. So here it improves the COP, and ultimately it reduces the compressor load, and the refrigerant stays in liquid form. The compressor handles less vapor volume, improving COP. So that is another advantage here, students. So here reduces the risk of flash gas formation, and it reduces the flash gas formation, and flashing of gas formation can be little eliminated, prevents premature vaporization before reaching the evaporator. And how liquid subcooling is achieved here is in the condenser by ensuring efficient heat transfer in the condenser, using a large condenser or enhancing its heat rejection capabilities, using separate subcooler. Some systems use an additional heat exchanger to subcool the liquid refrigerant before it reaches the expansion valve or throttling valve. So the pH diagram illustrates the effect of subcooling of the refrigeration cycle. So that is the pH diagram gives the entire idea on this. You can see the key observation here. The subcooled liquid refrigerant provides higher enthalpy difference in the evaporator, increasing cooling efficiency. So cooling efficiency is ultimately a desirable workout here. And the limitations of subcooling, if subcooling is excessive, so it should not be more, and it may increase energy consumption in the condenser and pump. So pump and condenser will consume more energy, and it requires an effective cooling medium like air or water to maintain subcooling efficiency. And conclusion, if you see, subcooling improves the refrigeration efficiency, prevents unwanted flash gas formation, and reduces compressor workload. However, excessive subcooling may lead to higher energy costs and may not be worthwhile. Subcooling, excessive subcooling is not worth enough, depending on system design, and it should be optimum, and that should only that optimum subcooling can be applied here, and more than that is not desirable. It gives unwanted load to the compressor and other accessories, condenser and pump. So that should be avoided. So the superheated vapor after compression. So after compression during the evaporation process, when you superheat the vapor, then the liquid phase will be little delayed. The vapor compression cycle VCC is widely used refrigeration cycle where refrigerant undergoes phase changes to transfer heat. So refrigerant initially it will be in vapor form. After compression during condensation process, it transforms into liquid form. So this phase change is very critical. In this version of the cycle, the refrigerant is superheated after compression, which impacts system performance. So this is the condensation process from 2 to 3. So this diagram is pH and TS diagram, and during condensation process this superheated vapor is having the effects that we are seeing here. There are four processes in this cycle. The first one is evaporation. During evaporation, we are applying the superheated vapor. So we start from 4 to 1. The refrigerant absorbs heat from the surroundings, leading to vaporization at constant pressure. So this occurs in the evaporator. And the compression process 1 to 2, this is the vapor is compressed, increasing its pressure and temperature. In this superheated cycle, the refrigerant becomes superheated at the end of compression, that is point 2. The degree of superheat can be found using entropy balance between states 1 and 2. So condensation process 2 to 3, the superheated refrigerant rejects heat in the condenser. So superheated refrigerant rejects heat in the condenser, and where the phase transformation is initiated. The first, if it first cools down the saturated vapor state, so that is point 2 dash, then condenses into liquid, that is point 3, and the expansion process takes place later. So in expansion process, the high pressure liquid refrigerant undergoes isenthalpic expansion. So the enthalpy is constant here. Isenthalpic expansion in an expansion valve. So this results in a mixture of liquid and vapor at a lower temperature and pressure. So here at lower temperature and pressure. So these are the four processes taking place, where in during evaporation process, during the condensation process, the superheated vapor playing the major role. So coefficient of performance is affected in this way. The COP is measure of efficiency of the refrigeration cycle, and it is given by refrigerating effect by work done. So in enthalpy pH cycle or pH chart, it is given by H1 minus H3 divided by H2 minus H1, where the enthalpy of refrigerant at evaporator outlet, that is H1, and H3 is enthalpy at the condenser outlet, and H2 is the enthalpy at the compressor outlet. So effect of superheating here, it increases the refrigerating effect. Superheating increases the enthalpy difference, that is H1 minus H3, leading to higher cooling effect. So superheating increases the enthalpy difference. So that is H1 minus the difference between these two H1 to H3 is enthalpy difference, that is becoming more here, and increase in work done. So work done is the compression. During compression work, H2 minus H1 also increases because the refrigerant enters the compressor at a higher temperature. So overall COP reduction. So superheated vapor after compression always gives overall COP reduction. Since the increase in refrigerating effect is smaller than increase in work done, the net effect of superheating is lower COP. So that is the ultimate result here. The COP is getting reduced. While superheating can help in avoiding liquid refrigerant entering the compressor, which could cause damage, it reduces efficiency due to increased compressor work. So proper cycle design is needed to balance the effects of superheating. Like in subcooling, we should not subcool it more. Like here also, superheating should be maintained at optimum levels. And the textbooks, the best book for this topic, you can refer CP Arora. Apart from this, you can refer Rajput and other Kurmi books. Apart from that, we have the e-resources, NPTEL and Bright Hub Engineering. So Bright Hub Engineering will not give much information, but in NPTEL courses, you can download the material, you can get a lot of information from that also. So we stop here, students. We will meet again in next session. Thank you, students.